Now we will prove our inverse function theorem. Suppose omega is an open subset of Rn, and F is a map from omega to Rn C1. And A is a point in omega. And we assume that the determinant of the Jacobian matrix, that is the Jacobian determinant of F at A, is not zero. This means that the Jacobian matrix or the derivative of F at A, which can be considered as a map, linear map from Rn to Rn, is invertible. Okay, the linearization of the map F at A is invertible. We expect F to be also invertible. But of course, this can only be true locally. So we expect F is locally invertible. Okay, locally invertible. The precise meaning of locally invertible is this. F is a local diffeomorphism. Local diffeomorphism. That is, there exists a U open set containing A and a V open set containing B. B is Fa. So that F as a map from U to V is bijective. That is, it is 1-2 and 1-1. Therefore, it has an inverse map. The inverse map is also C1. Okay, so this is the inverse function theorem. So this statement, the existence of U and V, and the bijectivity of F, and the smoothness of the inverse, all this is the meaning of local diffeomorphism. Local diffeomorphism. Okay, I have a misprint here. Local diffeomorphism. So this is what we call the local diffeomorphism. Okay, we have introduced this concept in our last lecture. Now we just record the idea. The crucial idea is that the linearization at the point if is invertible implies that the nonlinear map F itself is locally invertible, meaning that it is a local diffeomorphism. Okay. So now we state our main theorem, the inverse function theorem. This is the most important theorem in the differential calculus of multivariable functions. Therefore, it is the most important one in our course. Okay, so the theorem is read like this: inverse function theorem. Omega is open subset of Rn. F is a C1 map from omega to Rn, and A is a point in omega. The Jacobian determinant of F at A is not zero. These are the conditions about our map F. Then the conclusion is that F is a local diffeomorphism. At A, at the point A. So local diffeomorphism means that locally it is a bijective map bijection. It is a map, so it has an inverse, and the inverse is also smooth. Therefore, the inverse map is also differentiable, and we also have a formula for the derivative of the inverse map. The inverse map, the derivative of the inverse map at the point of y is the inverse of the derivative of f at the corresponding x, the inverse matrix of the derivative of f at x. But x is the image of y under the inverse map. Therefore, this can also be written as inverse. This is true for any y in the neighborhood v. Okay. So this is the inverse function theorem, the statement of the theorem. Now we will prove this theorem because the idea of this theorem had been discussed a lot before. Okay, so we start the proof. Since the Jacobian determinant at A is not zero, and the f is C1. F is C1 means that the function x to the determinant of the Jacobian determinant at x is continuous. This function is continuous. The continuity of this function and the non-zero property at the point A means that near the point A, this is not zero. So this means that there is some epsilon positive such that the first is that f is injective in this open set U. U is actually the epsilon neighborhood of A. And for some lambda positive, we have fx1 minus fx2 lambda x1 minus x2. This is the local stability lemma we proved last time. The Jacobian determinant at A not zero implies the existence of this epsilon under the lambda. Okay, for any x1, x2 in U. Now, the continuity of this function also implies that once x is close to A enough, once the distance of x to A is small enough, that is, once the epsilon is small enough, then for any x in this epsilon neighborhood of A, that is our U, we have the determinant at x is not zero. So therefore the image of U under our map F, V equal Fu is open subset of Rn, and moreover, B is a point in this set because A in U, B is Fa mass in Fu, that is V. So this V is an open subset containing the point B. So we already obtained the set U open set containing A, and V open set containing B. We already obtained this pair of open set containing A and B respectively conformed in the theorem. We want to prove the existence of such U and V. Now we already obtained this pair of sets. Now we want to show that f as a map from U to V is bijective. So it is already injective, right? Injectivity is guaranteed by this inequality. By this inequality, if x1 is not x2, then fx1 could not equal fx2. This means f is injective in U. So f as a map from U to V is injective, means 1 to 1. And of course, this is 1, 2, because V is precisely the image of U and F. Okay, so this map is 1 to 1 and 1, 2. That is, it is bijective. So it has an inverse map. So what remains to prove is that the inverse map of F is smooth. Okay. So we already know that F is 1 to 1 and 1 2, so it has an inverse from V to U. So what we need to show that the inverse map is smooth, it's differentiable. Okay. Now how to prove this? For simplicity, we denote the inverse by phi. Then this is a map from V to U. Okay. Now we prove that phi is smooth. And this property, this inequality, precisely means that this inequality, the stability of F, the local stability of F, precisely means that phi y1 minus phi y2, that is x1 minus x2, not greater than 1 over lambda fx1 minus fx2, that is 1 over lambda y1 minus y2. So this means that the inverse map is smooth, is continuous. So from the stability inequality, we already know that the inverse is continuous. So continuity is already known. This is already known. We only need to prove that it is differentiable.